Hello and welcome to G Fun Facts Online. Have you ever looked at a spider's web and marveled at its strength? Or watched a gecko scurry up a glass window and wondered how it defies gravity? For 3.8 billion years, nature has been the ultimate engineer, running countless experiments through evolution, resulting in designs that are incredibly efficient, resilient, and sustainable. For most of human history, we've built things by melting, beating, and pressurizing materials. We've viewed nature as a resource to be harvested or an obstacle to be overcome. But that's changing. We are now entering an age where we're looking at nature not as a resource but as a mentor. We're finally learning to read its blueprints. This is the world of biomimicry, the science of building our future by learning from the genius of biology. Today, we're going to explore the cutting edge of this field, but we're also going to look past the hype. What are the immense challenges we face in trying to copy nature? What are the ethical minefields we must navigate? And what does a future built with biology truly look like? Let's dive in. The promise of biomimicry is all around us. Think of buildings that cool themselves without air conditioning, inspired by termite mounds, or medical adhesives that work like a gecko's foot, or even materials that can heal themselves, just like our skin. These aren't just fascinating ideas. They represent a fundamental shift in how we solve problems. But translating nature's genius into human technology is far from simple. The first and perhaps most humbling challenge is complexity. Nature's designs are almost never for a single purpose. They are multifunctional, integrated systems that have evolved over millions of years. Take the gecko's foot again. It's not just sticky. The foot is covered in millions of microscopic hairs called setae. Each seta splits into hundreds of even tinier tips called spatulae. This structure allows the gecko to stick to surfaces using intermolecular forces known as van der Waals forces. But it's not just about the chemistry, it's the entire system. The structure of the hairs, the flexibility of the foot, the way the gecko engages and disengages it with a specific peeling motion. It's a masterclass in physics, materials, science, and robotics, all rolled into one. When we try to replicate this, we often simplify it, and in doing so, we can lose the magic. We might create a material that sticks well, but it might get dirty easily and lose its adhesion, unlike a gecko's foot, which is self-cleaning. Or it might not be able to support weight on a vertical surface in the same dynamic way. We are still learning to appreciate the deep, interconnected complexity of nature's solutions. This complexity leads directly to the second major hurdle, scaling up. Creating a small patch of gecko-inspired adhesive in a highly controlled laboratory environment is a monumental achievement. But the techniques used to do that, often involving complex microfabrication and expensive equipment, may not be economically viable for producing that same material by the square meter. Imagine wanting to create gloves and boots for a firefighter, or a search and rescue worker that would allow them to climb any surface. The difference between making a 1 centimeter square in a lab and mass-producing thousands of square meters for real-world applications is enormous. The manufacturing process needs to be completely reimagined to be fast, cheap, and reliable on an industrial scale. This is a common story in biomimicry. A brilliant concept that works perfectly at the micro level often hits a wall when faced with the realities of mass production. And that brings us to the bottom line: cost and manufacturing. Research and development in biomimicry is expensive and time-consuming. Scientists and engineers can spend years and millions of dollars studying a single biological system, with no guarantee of a successful, marketable product at the end. Even when a new biomimetic product is developed, it often has to compete with conventional products that have had decades of optimization to bring their costs down. A perfect example is self-healing concrete. The concept is brilliant. Researchers have embedded concrete with capsules containing bacteria and their food source. When a crack forms, water enters, the capsules rupture, and the bacteria activate. They consume the food and excrete limestone, which seals the crack, effectively healing the concrete and extending the life of the structure. This could save billions in infrastructure repair costs over the long term. However, right now, producing this self-healing concrete is significantly more expensive than producing conventional concrete. In the construction industry, where profit margins can be thin and decisions are heavily driven by upfront cost, this is a massive barrier. Until the cost of these new, smarter materials can come down to compete with the old, reliable and cheap ones, their widespread adoption will remain a challenge. So, we have the challenges of complexity, scalability, and cost, but the hurdles aren't just technical or economic. As we become more skilled at reading and using the book of nature, we must confront the profound ethical implications of what we are doing. The knowledge we gain from the natural world is a precious resource, and we have a responsibility to use it wisely and fairly. One of the most pressing ethical issues is biopiracy. This is the practice of taking knowledge from indigenous communities or developing countries without their permission and without sharing the benefits. For centuries, traditional communities have been the stewards of local ecosystems. They have an incredibly deep, generational understanding of the natural world, which they've used to develop everything from medicines to building materials. As large corporations and researchers from developed countries increasingly look to nature for inspiration, there is a very real risk that this traditional knowledge will be exploited. A company might learn about a plant's unique properties from a local tribe, develop a synthetic version in a lab, patent it, and make billions, while the community that held that knowledge for generations gets nothing. To address this, it is crucial that we establish clear and equitable guidelines. This means obtaining prior, informed consent from the communities involved. It means creating benefit-sharing agreements to ensure that they are fairly compensated and share in the successes that arise from the use of their knowledge. It's about moving from a model of extraction to one of partnership. Beyond biopiracy, we must also consider the potential for unintended consequences. Every new technology has a ripple effect, often creating unforeseen social and environmental problems. For instance, what if we develop a new biomimetic material that is designed to be incredibly durable and long-lasting, inspired by, say, the shell of a deep-sea snail? That sounds great for creating products that don't wear out. But what happens at the end of that product's life? If that super durable material is also incredibly difficult or energy-intensive to recycle, we may have simply traded one product lifespan, for another, bigger one, a new kind of persistent waste that clogs up our landfills and ecosystems. To mitigate this risk, we need to take a holistic and long-term view. This is where something called a life cycle assessment becomes critical. It means analyzing the full environmental and social impact of a product, from the extraction of its raw materials, its cradle, all the way through its manufacturing, use, and eventual disposal or recycling, its grave. Nature operates in cycles. There is no waste in a forest. Everything is a nutrient for something else. If we are truly going to learn from nature, our biomimetic designs must also embrace this circular principle. So with all these hurdles, complexity, cost, biopiracy, unintended consequences, you might be thinking this all sounds a bit daunting. But despite the challenges, the future of biomimicry is brighter than ever. And that's because we're developing powerful new tools that are making it easier and more affordable to study and replicate nature's designs. Advances in fields like nanotechnology, 3D printing, and especially artificial intelligence are accelerating discovery at an incredible rate. AI and machine learning are revolutionizing how we do science. These tools can analyze vast amounts of data, identifying patterns and relationships that would be completely invisible to a human researcher. In biomimicry, AI is being used to scan through enormous databases of biological structures. A researcher can input an engineering problem, say, I need a material that is lightweight, strong, and absorbs impact. And in I can sift through the structures of bird skulls, beetle shells, and plant stems to identify the most promising natural models to study. It doesn't stop there. Machine learning can then be used to optimize the design. It can run thousands of digital simulations tweaking the geometry or material composition of a bio-inspired structure to create something that is potentially even better than the natural model for a specific application. This partnership between human creativity and artificial intelligence is dramatically speeding up the process of discovery and innovation. This brings us to a vision for a truly bio-inspired future. As we continue to learn from the genius of nature, we are moving toward a world where our materials, our buildings, and our entire systems are in harmony with the natural world. Imagine cities that function like forests, where buildings capture rainwater like leaves, purify their own air, and are powered by the sun. Imagine industries that operate in closed loops, where the waste from one process becomes the raw material for another, just like in a natural ecosystem. Imagine products that are designed from the start to be safely and completely recycled and reused at the end of their life. This is a future where we are not just inhabitants of this planet, but true partners with it, a future where we have finally learned to build with biology. In conclusion, this journey into the world of biomimicry is more than just a quest for new gadgets and better materials. It is a fundamental rethinking of our relationship with the natural world. For too long, we have seen nature as something to be tamed, controlled, and exploited. But as we stand on the precipice of a new material age, we are beginning to see nature in a new light, as our mentor, our guide, and a source of profound wisdom that has been 3.8 billion years in the making. The lessons are all around us, in the elegant architecture of a seashell, the intricate dance of a flock of birds, the silent efficiency of a forest. By learning to read and interpret these lessons, we can create a future that is not just more technologically advanced, but also more sustainable, more resilient, and ultimately, more beautiful. The path ahead is not without its challenges. The complexity of nature is humbling, and the task of replicating its genius is a formidable one. But with each new discovery, with each new bio-inspired innovation, we are moving closer to a future where humanity and nature are not at odds, but are partners in a symbiotic dance. This is the promise of building with biology, a future where our creations are as elegant, as efficient, and as life-affirming as the natural world that inspired them. A future where we have finally learned to live in harmony with our planet, not as its masters, but as its humble and grateful students. Thanks for tuning in to Fun Facts Online.